All right, good morning, everyone. Um, let's start off with our exercise of today. So, last class period, which was on Friday, we did not meet live, but I did send you all some links for videos for you to watch. And so that covered that class, which was basically just finishing to interpret um, I guess, how our management zones were related to the soil properties and also how they were related to the yield. So both the coefficient of variation and also the mean yield across 3 years. And something that I just want to, I guess, point out, I think on the video I did bring this up uh, when that class was taught, was that on my side, um, like when we were doing the validation of the zones, you would see that perhaps zone one was low yield and zone two was high yield on my side. It may have been flipped on your side because of the k-means and how it operates with that random selection of the starting points. So even though our results in the end probably looked very similar, but still zone one or two could mean the opposite on your side than what it did on mine. And the place on the script where that would have made a difference when we were exporting that zone vector GeoJSON2 file. I just want to show you here. So on that management zones exercise where that would have made a difference. I'm just launching that that script again. So as you follow this in class, this is where it would have made a difference. So if on your side, if zone one was high yield, then you had to change this part of the code here just to make sure that you were properly classifying clusters. Because remember that we first had cluster 1 and 2, and then we wanted to give them context, so give them meaning. Then we did that looking at the yield data, which again, this was all through the video that I shared with you. And I guess actually on my side here, it seems like zone one was high yielding and zone two was low. But anyway, so as long as you made this coding here according to what you saw on your data, then we should be fine. And even if you didn't, we're gonna find that out soon. And if you did make the flipped selection, then we're gonna be able to fix that. But just wanted to point that out. All right, so this was the 11 management zone project, which we wrapped up with the videos of last Friday. I sent you earlier this morning an email asking for you to create this 12 zone VRN project, and then to create the subfolders, code data and output, create the RStudio project at this level, and also get the new code from GitHub and move that into the code folder of this exercise. I'm assuming that you all did that. If you did not do that, please go ahead and do it. I'm gonna get started with this, where we have an introduction part of it that's gonna be just talking about the topic, and so we can catch up during that time. If you're ready at this stage here, just go ahead and launch that 12 zone VRN project. We're gonna get started with that exercise. And then you can go ahead and launch your partial scripts that you brought from GitHub. All right, so let's just do a very quick recap of what we've done, where we are now. So we brought in yield data from 3 years, we processed that, merged them, did the spatial temporal yield stability exercise, and then we used our, so then we also brought the soil variables as far as the terrain in the form of elevation as our primary layer there, and use that primary layer to create the secondary layers of slope, aspect, flow direction. We also brought in electrical conductivity data from various, interpolated it, exported as 2 depths, and then we merge all that into the same file, created the zones. We smoothed the zones, as you saw that in the last exercise was an important step, and exported the zones. And we also So if you just remember here, we kind of had two approaches to zones. One was solely based on yield. One was solely based on other variables like soil and terrain. So we validated both of those, understand how yield and soil variables were related in this field. And now the next step here, which is what we're going to start today, is to use the zones that we created, so the high and low yield zones, and use that to create a variable rate prescription of nitrogen application for this field. So we're going to have a scenario here where we're going to have a specific crop, specific way of determining the rate, but it's going to be in the end a variable rate map based on the zones that we created on the previous exercise. So it's important that you do make sure you finish that exercise that we went over the video on Friday, because we're going to be bringing that here. And, also, I hope that you're noticing that everything is connected, right? All the way from the beginning where we started with the yield data until this point, all those layers are connected for this field. So we bring something, we process, we create something new, and then we keep using that in this workflow. Okay, so getting into the specific learning objectives of today, we're going to learn how and where to find crop-specific nutrient recommendations. Then we're going to understand what information is needed to make a recommendation of nitrogen in cotton. We're going to estimate the zone-specific cotton yield potential. We're going to talk a little bit more about that and why we're doing that. Use that to calculate the zone-specific total nitrogen recommendation, which is going to be in pounds of N per acre. And then we're going to transform that into a zone-specific side-dress variable nitrogen recommendation, both as nitrogen rate, but also as a product rate, right? So even though we're calculating things on a basis of a nutrient of nitrogen, pounds of nitrogen per acre, we still need to transform that to a product rate, which is what the grower is actually going to want to see and need whenever they're making their application. Also, based on that, we're going to calculate how much total fertilizer that grower is going to need for that application on that field. So the grower is going to have to order fertilizer to be delivered at the field so they can make this application. We're going to calculate what's the minimum amount of fertilizer needed for this field. And then finally, because again, the goal here is to create a variable rate map that a grower, or maybe you in your research, if you have a variable rate controller equipment, you can use in your research. So we're going to export this as shapefile for maybe the first time in this course, because again, that's the most used format in industry. And GeoJSONs are helpful for us when we're working with our files, just to keep things more tidy. But shapefile is still the one that we want to send to a grower for them to use. All right, so let's talk a little bit about this specific case here. Now that we know what we're going to be exploring today with the learning goals, let's see what we're doing more specifically with this exercise. So the goal today is for us to create a variable rate recommendation to apply nitrogen in cotton with different in-season side dress rates for each one of the zones. So if you think about it, in cotton and many crops grown in Georgia, normally nitrogen is applied at least split in two timings. So one is at planting or near planting, the other one's going to be a side dress. And that side dress application is really just an in-season application that matches more closely where the crop starts to require more nitrogen, right? If we apply everything at planting, we are at higher risk of losing that nitrogen. So let's say if you have a heavy rainfall right after planting, the plants are still so small, perhaps not even emerged. They're not really taking up nitrogen. So the nitrogen is just sitting there. And if you have a sandy soil and heavy rainfall, you may have a lot of nitrogen losses, meaning that maybe you applied 100 pounds of nitrogen per acre. Maybe you lost, losses can really range from anywhere, let's say from 10% all the way to 60, 70%, depending on the condition. So to make sure we don't over apply at the beginning and maybe have a higher risk of losing that through environmental losses, we apply a portion of that at planting and a portion at side dress at least. So our goal is going to be to calculate a variable rate side dress nitrogen for our different zones. Okay, so my question to you is, how do we know how much nitrogen, in this case, cotton needs Or really, if you just want to generalize that, how much nitrogen do we know, or how can we know how much nitrogen any crop is going to need? In this case here in Georgia. So if you are doing research, if you're working in a farm and you're following recommendations, sometimes industry has these recommendations, but the most trustworthy source, unbiased source of recommendation would be the universities, right? So each state, all the states in the US have at least, well, they have a land-grant university, meaning that is the university that most commonly does applied ag research. Here in the state of Georgia, UGA is the land-grant university that does this type of research, and we have a lot of extension data out there to help us to learn how much of any nutrient we need to apply to any crop grown in Georgia. So again, you could look for this in research papers, but normally extension publications and bulletins are going to be the best source of that information. And yeah, at least in the US, there's a lot of really great information on our extension side of publications from our universities. So let's say if this is a new crop for me, or maybe I'm new to Georgia, I have no idea how nitrogen is recommended here, and I want to learn that, you can just do a very quick Google search. I just have here an example of cotton nutrient recommendation in Georgia. You're going to be able to find a lot of great resources. If you do look for that, in this, again, I do have the very specific board in Georgia here, or the words in Georgia in the sentence, because every state has their own recommendations. And we do want to use, the algorithm that was developed for the state you're in, because that was developed through research done in that state, right? So let's say if I just Google cotton nutrient recommendation in the US, you may get something from the Midwest that's going to be perhaps very different from the conditions we have here in Georgia, both as far as weather and soils. So we want to be specific to the region we're in. So if we just do this quick search here, you're going to find a few results. And I'm not going to necessarily show you that directly, but if for any crop here in Georgia, you're looking for some algorithm to recommend nutrient, you can just do some similar search like this. So here in Georgia, we have, specifically for the case of cotton, we have a cotton team at UGA that works across the board with all different management practices in cotton and does a lot of field research to provide data that feeds into these algorithms. And a very nice publication put out by UGA is the Cotton Production Guide. I know there's also like a soybeans production guide, a corn production guide, a peanuts production guide. I'm not quite sure about other crops, but I would imagine that they all have their own production guide. So in this case here, specifically for our example, the cotton production guide is a very, very useful source of information if you're growing cotton in Georgia. If you're a grower and you want applied information on any recommendation or advice of all sorts of management practices. So I have here the link. I'm just going to copy this link and paste in my browser. So I'll show you how that looks like. This is updated yearly, so we may be getting a 2024 at the end of the year. But it's a very extensive publication that if you look at table of contents, it goes from economic situation and market outlook, it goes through fertilization of different nutrients, weed management, weed control, response to burn down herbicides, variety selection, planting dates, insect management, irrigation. So there's a lot of really great information here that goes across the board for all management practices that you may want to learn more in any specific crop. It's a very extensive publication. In our case, we are interested in nitrogen, right? So let's say if I'm coming here and I want to know how much nitrogen I should be applying to my field, you will come here on page 8. Starting on page 8, there is a nitrogen component there, right there. So most of the time, the way that nitrogen is, or the way that the nitrogen algorithms are developed is you would go, so let's say the team here at UGA went to many places, like many sites in Georgia, many years, and ran studies where they would apply increasing rates of nitrogen, and then in the end, just harvesting for yield, and then finding out what was the nitrogen rate that most commonly optimized yield. So because there is this relationship here between how much nitrogen you need to apply in order to get a certain amount of yield, they provide this table here, which is this overall relationship. So you set up a yield goal first, right? So let's say here we have a table with 4 levels of yield goal. And for each one of those levels of yield goal, in this case of pounds of lint per acre, you should apply this amount of nitrogen total on your crop. Now, the way that this works is, as you can see, the higher is your yield goal, the more nitrogen you would be applying to your crop to achieve that yield goal. But then there's a few places here where it changes the rate. So you first calculate your total rate here, and then it has, if you look below here, there's a few conditions. So you should increase your nitrogen rate by 25% if you're in a deep sandy soil, you have cotton following cotton, or you have a history of inadequate stalk growth. Similarly, you should decrease your nitrogen rate by 25% if you have cotton following peanuts or soybeans. That's because peanuts and soybeans are fixing nitrogen, and there is an assumption of a nitrogen credit coming from that peanut or soybean crop into the cotton crop. If cotton following good stands of winter legumes such as clover or vetch, same thing here. Winter legumes fixing nitrogen, you would assume you have some level of credit from those previous crops, or if you have history of rank or excessive vegetative growth. So cotton is, I mean, if you've never worked with cotton, it's a little bit of a different game as far as nitrogen management, because for most row crops, at least, that require nitrogen, you will, as you increase your nitrogen rate, you may increase your yield as well until you reach a plateau level. And after that plateau, you really need to apply a lot more nitrogen before you start seeing a decrease in yield. So like a toxicity effect of nitrogen on the crop. In the case of cotton is a little bit different because cotton is actually a perennial crop that we annualize. Meaning that if you apply too much nitrogen, it's going to want to grow and become a tree and not give you fruits or not give you bolls or flowers that turn into bolls. In that case, this is what rank or excessive vegetative growth means, is if you are in a field where you have conditions of that field that are already conducive for the crop to grow like a tree and not give you bolls or flowers that turn into bolls, you don't want to over apply nitrogen and make that even more vegetative growth in that case. So these are just some of the conditions here that we have for how we would determine the rate of cotton. And again, this is in the EGA Cotton Production Guide, that in Georgia is the best source for cotton. So we can see here that the total nitrogen that we would apply will depend on the yield potential first. So we go to your field and determine what is my yield potential of this field. Now let's just make a distinction here. Yield potential is not just what you wish you would get, right? So it's not like, well, I'm going to go to this field here and hope that I can make 3,000 pounds of lint per acre. If you've never made that yield before, right? So let's say your yield average is, 1,500 pounds of lint per acre. You're probably not going to get 3,000 pounds of lint per acre in this field. That is not your yield potential. That perhaps is just wishful thinking. So what we need to determine here is a appropriate yield potential level, and we're going to talk a little bit more about that in a second here. So beyond yield potential, we're going to be adjusting that nitrogen rate in either plus or minus 25%, depending on the conditions as we just saw. And also, I guess I did not cover this from here, but so this sentence here, the total nitrogen rate. So determine the total here. You change that according to these conditions. And then the total nitrogen should always be applied in split applications. So about 1/3 to 1/3 of the total recommended rate should be a planting and the remaining as side dress. And in the case of cotton, side dress basically means between first square and first bloom. So coming back to our script, so the total nitrogen will depend on the yield potential. It should be adjusted given those conditions, and it should also be split applied, right? Another really great, so this type of information is really common across crops, across states. So every state is going to have a similar production guide. UGA has a very interesting tool that not every university has, which is called UGA Vertex. So if you've never heard of it, I do encourage you to use it. I left you the link there, and I encourage you to launch this on your site as well. So UGA Vertex is basically this web browser tool that was developed by UGA researchers. So Glenn Harris is one of them. He's a soil fertility specialist. Then his office is out of Tifton. He's done a lot of research in cotton and other crops, but in this case here, we're thinking of cotton, that they put together on this tool here called UG Vertex that we can really make use of, find our recommendations. So there's really a lot of tabs here you can explore on your own. I do want to ask you to come on the inputs tab, which is on the top. The things that we need to change here would be crop. So if you want to go on crop and select cotton, you can go ahead and do that. As you do that, you can see that it pops up a new table here on the bottom side with different information for nutrients, for different nutrients, not just nitrogen, but mostly PK. Let's see, yeah, PK, and then some other macro and micronutrients as well, along with pH and lime recommendations as well. So let's say in our case here, if we select the crop as cotton, you can see that the next box there has soil type, so coastal plain, Piedmont, and deep sands. We are going to select coastal plain for this field that we're in. If we were in North Georgia, like we're here in Athens, you would select Piedmont, and if you have deep sands across the state, especially on the southern part, half of the state, you would select deep sands. Another thing we have to change here is the prior crop. So let's assume that we're doing a cotton after cotton. So let's prior crop, let's say it was cotton as well. And let's see what other. Okay, so let's also, so this field that we're working with is irrigated. So there's an irrigated box that we can check that box, make sure you check that. And then we have this EO goal here, which is in pounds of lint per acre. As you see right now, the default value it gives you is 1,000 pounds of lint per acre. And for that amount of nitrogen, or sorry, for that amount of yield, it has a recommendation of 75 pounds per acre of nitrogen. Just to give you some more information, if you have not used this tool before, and you would also like to get recommendations for phosphorus, potassium, and other nutrients, what you would do is basically run this on a soil test. So you collect soil samples, send them to a soil test lab. They will analyze for you, and you can enter those numbers that you get back on the soil report here on the P2O5, pH in water, target pH, and other. Let's see, I'm not seeing here a potassium. But anyways, you enter your results of the soil test here, and then you get a recommendation back as well. Okay, so focusing on nitrogen again, so coming back to our example. So the default yield that we got here was 1,000 pounds per acre, 1,000 pounds of lint per acre. What happens if we change this 1,000 to 500? So do on your side, let me know what you see. Ujjwal, what do you see there? It didn't change? Anyone had luck? Doug did that. 45 pounds, right? So if you change the 1,000 pounds of lint per acre and you look at your nitrogen, it's going to decrease, right? So 45 pounds per nitrogen per acre if you have a 500 pounds of lint per acre of EO goal. We originally had 1,000 here, which was given a 75 pounds. And similarly, if we change now to 1,500, this rate is going to increase, right? So it's basically just this linear positive relationship of the higher yield goal you have, the more nitrogen going to be applying to this field to reach that yield goal. So I really recommend that you bookmark this page here if you're working with crops here in Georgia, because this, as you saw, has a whole bunch of crops that you can choose in your inputs, and it's going to provide you information on any of those crops. So it's really useful tool from our extension faculty. All right, so I have a quick quiz for you. So let me go on my ELC and let me activate that so you can see the quiz. All right, so the quiz was just made visible. Make sure you answer it. I'm going to give you 5 minutes here for us to go through it, and I have two questions for you. So one is list at least 3 required pieces of information needed to make a recommendation of nitrogen in cotton. So we just talked about that. And the other one is so yield potential is the main factor affecting recommended nitrogen rate. How can we define yield potential for each of the 2 zones? I want you to answer this based on the data that we have for this field. So think about the layers we used and how would you determine yield potential for this field? I'm going to give you 5 minutes here. We're down to the last 50 seconds here. All right, time's up. Make sure you wrap up your submission. All right. So I was checking a few of your answers here, and I just wanna talk about it a little bit before we get into the exercise. So one way that we normally think of yield potential, and I think some of you, the ones I checked, I saw this answer in there is, so we do have yield data from this field, right, for 3 different years. So we have some idea of how yield varies across this field. We could use that, right? So that is a piece of information we can use here. And normally what we would do is we want to use so thinking that this is the yield potential of the field, the mean doesn't necessarily represent the potential, right? The mean is more of like the mean, right? So the mean of that field represents on average what you're getting from that field. But if you think of potential, you want to push a little bit that boundary there and not necessarily use the mean. So something that people normally use is, let's say, the 90th quantile of your yield distribution across many different years. So that's what we're going to do here. We're going to bring back the yield data. We need to, so if you think with me here, if we bring back the yield data for 3 different years, imagine that we have 3 columns, one for yield on 2017, 2019, 2020. We also need to merge that with the GeoJSON and the object that has a column for zone. So either low or high yield, right? Because we want to group by zone and then calculate the 90th quantile of the yield distribution across 3 different years. So that's the data set we need to envision here that we need to be able to calculate this. So let's go ahead and start doing this then. I left you here all the packages. You can just go ahead and run that chunk. You should have all those packages already. The next chunk here is just our theme that we've been using for the map. You can just run that as well. Now, on the steps we're going to do next here are going to be to bring back those yield layers that we had. So not necessarily the mean yield, the mean standardized yield or the mean CV, which are products that we calculated when we did the spatial temporal analysis. We need the actual yield values. So if you remember, we had those layers. Let's bring the first one here for 2017. So I left you the name of the object. You can just give the assignment symbol. That was an SF object. So let's do a read_SF. Let's navigate to that. So if you remember, open and close quotation marks, all the yield data that we created was exported on the project that we had for yield. So we need to do .. to get outside of code. If you hit tab, it should be on the main folder of this project. Another .. to get the main folder of your course. And now this should be under your 07 yield monitor. That's where we had all the yield data processed. If you hit tab, it should navigate to the data folder. And here we want to bring in the yield 17 interpolated.geojson. So we want to be the interpolated. If you remember, the interpolated was where we already applied the wrangling steps, we already applied the yield filters. And we also interpolated that afterwards with our grid. So this is the one that we want to bring. If you run that and we print it, we have these two. So in my case, 4,046 rows, which is again what I expected for this field on my side. And then we have this IP yield underscore pump breaker and the geometry. What I just want to do a quick rename here on the go. So if you give this a pipe right after right after the read SF, let's use dplyr ::select, and I want to call this yield 17 underscore LBAC for pump breaker. And I want to say that this new column I'm creating is going to be this equal to IP yield pump breaker. So if you do that and you run it, now that EO data was renamed to EO17 pump breaker, and you still have the geometry there. If we do a quick check here on the panel, on the first panel of the print of this object, it is projected, it is in UTM, so good thing. That's how we exported it. And if we just get a summary here, we're going to be able to see that yield for this year range from about 300 to almost 2,000 pounds of lint per acre. All right, so we brought in the 2017. I left you, if you go to the next chunk, I left you the same code for the 2019, which is just navigating to that same folder and getting the EO19 interpolated. If for some reason you rename things differently than me, you're gonna have to change and according to your name files, right? So this path works on my side. If you follow the name conventions that I had, it should work on your side as well. But if you didn't, that's okay. You just have to adapt this. The goal is to go to that 07 EO monitor project inside the data folder and get the EO19 interpolated.geojson. And then we're just renaming that IP EO pump breaker to EO19 pump breaker. So then we're gonna know exactly if the yield is coming, what is the year the yield is coming from. So here we have yield 19, here we have yield 17. That way we're gonna know exactly. Make sure you run this chunk. So we're gonna check here. We do have ETM NAD 83 like we wanted, and we also have our yield 19 pounds per acre. If we ask for a summary, just very quickly, we're gonna see here that yield was ranging from about 100 pounds of lint per acre all the way up to over 3,000 pounds of lint per acre. So 2019 was a better yielding year, seems like, at least on the maximum side. And then lastly, if you go to the next chunk, we're doing the same, but for yield 20, right? So we're bringing that as yield IC20, meaning that it was interpolated. And then again, just making sure we change the object here to be that yield 20 interpolated, just to rename it appropriately as well to reflect the year. If you just run that, it should work. Again, if it didn't work, you're gonna have to make sure you find your path to this file here. If we just printed UTM and 83, great. Proper number of rows, 4,046. Let's check the summary. Yield ranging from about 400 pounds of lint per acre up to 1,755. All right, so we brought in all the yield data that was Sprengel, clean, interpolated. So if you're keeping track here, each one of these files have one of those columns that we need, right? So we need yield across each one of the years, and then we need another column that is going to be the zone column, right? So we can get the 90th quantile for each one of the zones. So if you come here to the next chunk, we're going to bring in the actual zone, the actual zone shape file or GeoJSON file that we exported from the previous exercise. So again, this chunk here depends on you completing the exercise that we had on Friday, because we exported this at the end of that exercise. So if you come here, let's call read SF again, as this is an SF object. We need to navigate to that project. So that is // to get outside of the code folder, another // to get outside of this project. We navigate to the 11 management zone. We go into the data, and then there we have the zone underscore s.geojson. If you run that and you print it, so this object here, again, has 4,046 rows, which is what we wanted. We also have a lot of data here that we don't fully need at this point. So really, the only thing I need from this object here is a column that has the zone information and the geometry. That's all I need. So to keep things simpler, let's do a dplyr select. And only select the column. I think the last column here is called zone. Let's just make sure that's correct. Yep, let's just select zone. And I think the geometry is just gonna come already. So let's just keep to just, let's just try to select only zone and see what happens here. Yeah, so now we have zone and geometry. That's what we needed, right? So now we have 4 different objects where each one of them has one piece of information that we need to calculate the EO potential across 3 years for each one of the zones. If you come to the next chunk, I left you the code already since we've done this a handful of times by this point. Just to show you here, what we're doing is we're starting with the zone. So zone ST, we're starting with that one. And then just doing an ST join on EO 17, 19, and 20. If you run that, and you print this object that we just created called zone yield, we should have the 4,046 rows, at least on my side, and then we have the zone. The geometry is going to be there, of course, and then EO 17, EO 19, EO 20. Right? So that is what we needed to have all in the same object. So now we can calculate our EO potential for each one of the zones in this field. Let me take a quick moment here and make sure everyone was able to get to this point. Everyone is good.
Hello. I got there, but before when I pulled the zone SGeoJSON, I have 15 rows,
Okay.
not 14.
So you're gonna have to go back to the previous project and see what happened there. Yeah, we're not gonna have time to troubleshoot that in class. What I would suggest is that you go back, like after class, you go back to that script and try to troubleshoot yourself. If you cannot find what went wrong, let me know. We can connect in one-on-one.
Thanks.
All right. Any other issues here? All right, so if I don't hear anything, I'm gonna keep moving. I guess, Rolando, maybe for you, it's not gonna work. I mean, you can still code along for the remaining of the next 5 minutes. It's not gonna fully work on your side because you don't have the proper number of rows on the zone object, but yeah, but we'll make sure that that is working before next class. Okay. You know what? I think, let's see. Well, we can try to go through one step here, at least. Yeah, all right. Okay, so let's start working on our VRN here. So below, what we're gonna do is calculate the zone-specific EO potential. We're gonna take that as the 90th quantile of the EO distribution across all 3 years. So all 3 years together, we're not gonna just make a distinction between years. And I guess before I keep telling you here, I do want to explicitly mention something. I think it's really helpful, regardless of what software you're using, to try to create kind of like the vision of what you're gonna do, and to the best extent possible, try to determine the steps you're gonna need in words, just like, right, just using English words. And once you determine that, I think it becomes clear potentially of how you have to use coding or any other software to translate that into software. So I just, you know, I've been trying to do this throughout, but I just wanted to point that out here since we have this list in front of us, right? All right, so first step is going to be calculate zone-specific yield potential. Then we're going to calculate the total nitrogen rates needed with the UG vertex. We're going to adjust that in plus 25%, assuming that we're following cotton. We're going to adjust it in 2/3 to be applied side dress. So only 1/3 at planting, and we are only varying the rate at side dress. So at planting is going to be the same rate across the field. At side dress, we're going to be using our zones to determine the rates. Then we're going to define our nitrogen source as urea ammonium nitrate, which is a liquid fertilizer that in this case here, I'm proposing we use a 28% concentration, nitrogen concentration in this nitrogen source. And then finally, calculate the total product rates for each one of the zones. And I think that's where we stop on this chunk. Okay, so I first just wanted to visualize here the distribution of yield across all 3 years, depending on the zone. And perhaps this can be where we stop here. So I'm starting with zone yield, just to show you again. Zone yield has 4,046 rows. It has the zone, the geometry, and then the yield in 3 columns here for each one of the years. If I want to combine all the yield data under one column, I have to do a pivot longer. We've been doing this enough. I hope that you're already getting the gist of it. So I'm just doing a pivot longer here with saying the columns from yield 17 to yield 20. If I just run until this point, this is what happens. I have the zone, I have the geometry, I have a new column here with the previous column name, and I have a new column with all the values from those columns. Then I'm just feeding this into a ggplot where I'm putting the value. So this value column here as the X variable, and I'm making the fill by zone and asking for a geom density. If you remember, geom density calculates the y-axis for you, so you don't have to calculate that. Or you don't have to specify a y variable. That's why we didn't here. If you just go ahead and run that, this is the yield distribution of both the high yield and low yield zones for us. In my case here, this is one of those steps where you can check if you renamed your zones properly when you exported from the previous exercise. So we have yield is the value here, and then we have the distribution. Then, I mean, if we think of mean is probably going to be near the peak, you would like to see your low yield with a peak that's more to the left than your high yield. So if you're seeing something similar to this, then you code it correctly, your clusters to zones. If they're flipped, then you're going to have to fix that. So maybe going back to the previous exercise. Yep.
So the point is to be left, not lower. My low one, I think it is a little left. They're
Almost the same.
but the low one is a lot shorter.
Okay, interesting. So your low one should be more to the left because the left here, all the way to the left is 0 pounds of lint per acre, and all the way to the right is 3,000. So your low should be more to the left than your high, even if it's just by a little, but yeah. Okay, so I guess this is just doing some EDA, so exploratory data analysis on this. I think this is a good stopping point. In the next class, we're going to continue with this exercise and going through the actual recommendation. Let me get your attendance for today, and then you can be on your way. All right, I just opened the issue, so make sure to claim your attendance. And if anyone has any questions and you'd like to ask, feel free to do so. Once you take your attendance, you're good to go as well. I guess any questions? All right, I don't hear anything, so I think that's a wrap for today. See you all on Wednesday. Thanks.